Welcome to solverfy.
In this question, we're looking at radon gas. Now, radon gas, we are given decays via alpha decay. And we want to find what is the daughter nuclide. So alpha decay means we have a helium nuclide. And we have the unknown X over here. To find what is X, we look at the proton number and nucleon number, and we make sure that they are conserved from the left hand side to the right hand side. On the left hand side we have total of 86 protons, so on the right we must have 86 as well. Since helium takes up 2 of them, X must have 84 protons. Same with the nucleon number, so 222 on the left, 4 is taken up by the helium, so there should be 218 left, right? 218 nucleons. So looking up the periodic table for an element with 84 protons, we find that the element is polonium. Right? So this is our daughter nuclide. Now, daughter nuclide polonium from figure 30-11, right? It is a radioactive nuclide which decays into alpha and beta particles, right? It involves 2 different decays, and the half-life is 3.1 minutes, right? So it is a radioactive but nuclide, right? Now, the daughter nucleus is not a noble gas, right? The polonium is in group 6, right? So it's not a noble gas. It's the same group as oxygen, so it should be chemically reactive. Right? It can react with other chemicals and other elements. Now, to find the activity, we are given a source of mass 1.2 nanograms. So that's, sorry, not 1.2 but 1.4. That's 10 to the power minus 9 grams of radon. To find the activity, we will need the lambda, which is the decay constant, and the number of nuclides, n. For the decay constant, we take ln 2 divided by the half-life, where the half-life of radon gas is given to be 3.8235 days. 3.8235 days. We convert that into seconds, right? Multiply by 86400 seconds per day. The number of nuclides we can find by taking the mass 1.4 times 10 to the power minus 9 divide by the molar mass, that is 222 grams per mole, to get the number of moles. Then we multiply by the Avogadro's constant, right, which is 6.02 times 10 to the power 23 to find the number of nuclides. From this, we should be able to get an activity of 7.964 times 10 to the power 6 decays per second. Now, the decays per second basically is in terms of becquerels, right? So this is equals to about 8 times 10 to the power 6 becquerels. Next, we want to find the activity after a month, right? So to find the activity after a month, you use the decay law to find what is the activity. So this equals to the initial activity multiplied by the exponential, the power of negative lambda t. So in this case, the initial activity we already found previously to be 7.964 times 10 power 6, right? And the lambda is the same decay constant, which is ln 2 over t half, which is 3.8235 days, multiplied by t, and the t in our case is a month. Gotta assume that it's 30 days, so that's 30 days. So now we don't have to convert the days into seconds since we are all dealing with days. Just substitute the values in. We should get 3.465 times 10 power 4 days per second, or 3.5 becquerels, or 3.5 times 10 power 4 becquerels. Right, so this is the activity after a month.